All righty. Green's theorem. There are three classic theorems in vector analysis. This is one, Green's theorem. The second and the third we call the so-called Stokes theorem, and then thirdly the divergence theorem. All three are said to be one of one nature, that Green's theorem can be written in equivalent forms to Stokes and also to the divergence theorem. So we start with Green's theorem, and what he's concerned about is this: is it possible to relate a single integral to equal a double integral? Here, can a line integral be equated to a double integral? Both, you have the same values. If so, then is it easier to compute one or the other? Namely, is it easier to compute the double integral? Typically, it will. The double integral is based on how, you remember back in chapter 14, how we started, where we talked about vertically simple or horizontally simple region. So can we convert a line integral to a double integral using the regions from then x and y, and then just solve that double integral? If that's the case, then Green said that you can bypass evaluating the so-called line integral. What he notes is that you want to be able to do that for all line integrals that are said not to be conservative. If they're not conservative, then is there still an easier way? And Green says there is an easier way. And here, he equated the line integral. The proof is not difficult, very direct, but he computed that the line integral can be found by a double integral. And so he did have a criteria, and the criteria here is based on the region itself. Since you're converting, you're going from C to R, he's going from this curve to some double integral over R. Here, some partial derivative times dA. I don't think I got that written right. So he's making the jump from a curve to a region. But the neat thing is, when he gets to the region, he puts focus on the boundary of the region. He says the boundary of the region is the same as what's happening from the energy on the inside. He said, I can compute the energy from the heat, or I can compute the boundary, what's happened exhibited around the boundary of the surface. He said, whether I compute what's happening on the area or the so-called surface boundary, he said, I get one and the same. He says that what's happening along the boundary is equal to the line integral curve itself. But he makes the criteria. He says that I got to have what he calls a simply connected here region, and he defines here simple. Simple. Here a curve is said to be simple when it does not cross itself. And then a connected plane region is simply connected when every simple closed curve in R encloses only points that are in R. In other words, he says that if I have a path around a so-called region, that this curve does not cross itself, doesn't double loop, and that everything in the path stays within the region. So basically this becomes a true boundary, is what he's really saying. This is in the 2 dimension. So he says you don't want to have this. You don't want to have what's happening in R2 where this is said not to be simply connected, or in R3. So we get the nature of connectedness going back to the so-called independence of path, but then he puts this other criteria of simply connected. And so he says that if you have the simple connected region, then you can compute the area if you want, or you can look at what's happening along the boundary itself. And he says that both energies, in terms of the work, is said to be equivalent. Here's what he says formally. He says, let R be a simply connected region with a piecewise smooth boundary. He's concerned about the boundary. C, oriented counterclockwise, that is, C is transverse once so that the region R always lies to the left. If I could go back here. So as we travel along this path, traveling counterclockwise, the region is always to the left of the boundary curve, right? So he's walking, going along a path, and this is the region here, always just like that. I don't know if you remember, y'all didn't do this, but back when I was in school, like in the, I don't know, 3rd, 4th, 5th grade, we would like fight, but we really didn't fight. But we just go all day in a circle like that. What you gonna do? What you gonna do? What you gonna do? His shoulders like right here, What you gonna do? You remember that, Man, you ain't nothing, man. You ain't nothing, man. And I'm praying, where's the teacher? Man, before this guy gets me, man. Because I do a lot of talking, but that was about it. So, well, anyway, the curve, in terms of the boundary, the curve always lies to the region lies to the left of the curve, excuse me. So when you have that, now why does he use counterclockwise? Initially, what he was concerned about was that he was actually trying to measure the electric flow through a circuit, and electricity travels counterclockwise. So when you look at a circuit board, that's what he was concerned with, and so he says you can calculate the work on the region, or just look at what's happening on the boundary. It's just the same thing. Let's see. So this is the theorem. The line integral is the same as the double integral over the region with respect to the area. Right? Obviously, here, m and n must have continuous first partial derivatives because I'm using these first partial derivatives. Let's see. So find the line integral by evaluating the double integral. I think in the book it says compute both. I'm just concerned about computing the double integral. If you get the answer for the double integral, just put that answer for the line integral. It's still the same thing, right? So again, we're only concerned about the boundary of the region lying between the graphs of y equal to x and y equal to x squared. So we're looking for what's happening in here. Remember, going back to chapter 14, we take these two equations and we set them equal. So I get x squared minus x is equal to x times x minus 1 equal to 0. So I get x equal to 0 and x equal to 1. So the region is defined as x goes from 0 to 1, and then y goes from the curve x squared is below, so this is x squared less than or equal to y less than or equal to x. Now the partial derivatives here, remember this is m, this is n, so the partial of m with respect to y is 2y. The partial of n with respect to x here is 2x. Again, Green is not concerned whether or not the vector field is conservative. He's saying for those cases when it's not conservative, he's saying, use my method. Use my method. Okay. So according here to Green, this line integral becomes this double integral over the region of those partial derivatives now. This is 2x minus 2y dA. And we know what the area is based on the region. So we have the integral from 0 to 1, the integral from x squared to x, and this is 2x minus 2y, and this is dy dx. So we first integrate with respect to y. This is the integral from 0 to 1. This is 2xy minus y squared, where y is evaluated from x squared to x. This is dx. This is integral from 0 to 1. This is 2x squared minus x squared, and then minus 2x times x squared plus y, which is x squared to be squared, get x to the 4 dx. So this is the integral from 0 to 1. Let's see, 2x squared minus x squared is just x squared minus 2x to the third plus x to the 4. Now integrate that, x to the third over 3 minus x to the 4th over 2. 2 over 4 is just 1/2 plus x to the 5th all over 5. That's evaluated from 0 to 1. So we get 1/3 minus 1/2 plus 1 over 5. So here we got 3 goes into, I think that's the smallest number. No, I think there's a number smaller than that. $30. 10 minus 15 plus 6. So that gives us, what, 1 over 30? Okay. So can the line integral be computed by a double integral using the area that we talked about back in chapter 14? Well, Green says it is so if the region is simply connected. Let's see. Here's another one. It looks like the line integral is the same. Let me go back to this one. Is it y squared x? Yeah, y squared x squared. So good. So this guy is conservative. Well, not concerned about it being conservative, excuse me. Scratch that statement. But those partial derivatives that we needed here, we still use. This is the double integral over the region. The partial of n with respect to x is 2x minus the partial of m with respect to y is 2y dA. Now we have to determine the region. Here I have y equal to x, and then I have y equal to x squared. Now the graph of that, y equal to x, is going this way, and the square root of x does that, right? So this is y equal to the square root of x, y equal to x. So the curve now is on top. So I set x equal to the square root of x, square both sides, we get x squared is equal to x squared minus x is equal to x times x minus 1 equal to 0. This implies x equal to 0 and x equal to 1. So the region here, x goes from 0 to 1, but y goes from the bottom, x, to the square root of x. So this line integral is equal to that double integral from 0 to 1, x to the square root of x, and this was 2x minus 2y, dy dx. So I think we have that right. Yep, 2x minus 2y. So evaluate with respect to y, the integral from 0 to 1. This is 2xy minus y squared. Y goes from x to the square root of x dx. It's the integral from 0 to 1. Replace the y now with the square root of x minus the square root of x to be squared. Then this is minus 2x times x plus y to be squared, but now y is x, so this is x squared. So here, we're not talking about conservative vector fields. It's not independent of path, so I don't expect to get the same value for this integral like I did from the previous one. So this is the integral from 0 to 1. This is 2x to the 3/2 minus x minus x 2x squared plus x squared dx. Integral from 0 to 1. Simplify that again. This is 2 times x to the 3/2 minus x squared dx. So we integrate this guy. This is 2x to the 5/2 all over 5/2 minus x squared over 2 minus x to the 3rd over 3. Evaluate that from 0 to 1. Well, this is 4 over 5 times x to the 5/2 minus x squared over 2 minus x to the 3rd over 3. Evaluate that from 0 to 1. Let's see, that gives us what, 4/5 minus 1/2 minus 1/3. We use 30 for our least common denominator. 5 goes in 36 times 6 times 4 is 24. 2 goes in 30. 15 times 1 is minus 15 minus 10. So this is negative 1 over 30. Okay. Let's see a couple more problems before we get out of here. This is a square with vertices 0, 0, 1, 0, 0, 1, and 1, 1. Oops. So this is x is bounded from 0 to 1. and y is bounded from 0 to 1 for our region. This setup is the same as before. So this is the double integral from 0 to 1, 0 to 1. We had 2x minus 2y dy dx. The integral from 0 to 1. This is 2xy minus y squared. Evaluate that from 0 to 1 dx. So this is for y. So this is 2x minus 1. That integral from 0 to 1 dx. X minus 1 dx. Now evaluate that at x. We'll integrate that at, with respect to x. So we get x squared minus x. Evaluate that from 0 to 1. We get 1 squared minus 1. Get 0. There's two problems here that I definitely want to work. I think this is one of them. And then the, yes, sir. Yeah, Green is not concerned about, closed loop value with respect to that independence of path. Yeah, it just happened to be, yes, sir. Yep. There are some, the other two problems were closed as well. Yep. It was the region was connected, contained. Yes, sir. Yep. So. Just a coincidence. So let's look at this guy. Here I need the partial of m with respect to y. This is m again. This is n. So the partial of m with respect to y is 1. The partial of n with respect to x is 2. And the boundary is of the region line inside the rectangle with vertices. So this is 5, 3. Looks like it picks up -5, 3, and -3. So this is 5, 3, -5, 3. And then down here, -5, -3, and 5, -3. Oops. And then inside there's a square. There's a square, it looks like a rectangle, but so you want the boundary of the region line inside the rectangle and outside the square. So here, it's just the area. So if I call this R1 and call this R2, now the area for R1 is equal to, let's see, this goes from 10 to 6, right? The length is 10, and then the height is 6, so that's 60. Right? 10 times 6. Then the area for R2 is, what, 2 times 2? You get 4. So this line integral is equal to the double integral over the region. Those partial derivatives come out to be 2 minus 1. Times dA. So this is the double integral with respect to the region of the change in the area. The area changes from 60 minus 4, just get 56. All this time is getting me. Can't do them all. Let's do this one. So for Green's theorem, I need to compute the partial of m with respect to y. This is -3, and the partial of n with respect to x is 1. So the boundary of the region lying between the graphs of two circles, one circle is radius 1, and then one circle radius 3. So we're looking for the wheel. Oh, what is that? So this region here, the radius goes from 1 to 3. And this is a complete loop, so theta goes from 0 to 2 pi. So I'm going to convert this single integral is converted to a double integral over the region of, this is 1 minus a -3, 1 minus a -3 with respect to the change in the area. Well, the area is being changed with respect to the radius in theta. So let's see here, 0 to 2 pi, the integral here 1 to 3, excuse me. And this is a 4. Polar coordinates, you got to have that r. Then this is dr d theta. So integrate with respect to r, the integral from 0 to 2 pi. So this is 4r squared over 2. It just becomes 2r squared. It's evaluated from 1 to 3. Excuse me. So this is the integral from 0 to 2 pi. This is 2 times 3 squared minus 2 times 1 squared d theta. So we get 9, 18 minus 2. So we get here 16 times the integral from 0 to 2 pi d theta, and that just gives us theta. Evaluate that from 0 to 2 pi, and we get 32 pi. There was 1, 2, 3, 4 problems that I skipped. They are important as well, and I'm over 2 minutes. Let me take one of those, set it up, and so I can show you something, and then from there, you should be able to go from there. Now, that one is number 9 is easy. That one is easy. I'm gonna set this one up in that number slide number 10 up for you, and then we'll go. I'm going to show you this. So you get those partials. The partial of m with respect to y is 2x, and the partial of n with respect to x is 1. Here for the region, I get y equal to 0, y equal to 1 minus x squared. I set both equations equal. So doesn't that imply when you solve for x, you get x equal to plus or minus 1? So if we look at this graph, so this region is defined from -1 to 1, and then y goes from 0 to 1 minus x squared. So this double integral, just going to go right to that. It's negative 1 to 1, then the integral from 0 to 1 minus x squared. Those partial derivatives, that gave us 1 minus 2x, and then this is dy dx. So you should be able to get 4 over 3 now, from there. Just want to set that up for you. Then I want to set one more up quickly, and then we'll go. I'll post this in just a minute in Blackboard, so you'll be able to see it as well. So here, the partial of m with respect to y is negative sine y. Then the partial of n with respect to x, that is y minus sine y. Now, this graph is y equal to x, and then that square root. So we had that one before. I think x went from 0 to 1, right? For these two guys right here, you remember? You set x equal to the square root of x. Get x squared minus x is equal to x times x minus 1 equal to 0. X equal to 0, x equal to 1. So the region goes from x 0 to 1, and then y goes from the line on the bottom, x, to that radical, the square root of x. Now this one is fun to work. When you work it, you'll see what happens. That is this double integral. You get from 0 to 1, and then the bottom is x, the top is the square root of x. You go back to the partial derivatives, it's the partial of n with respect to x first. So this is y minus sine y, then it's minus the partial of n with respect to y, and that's minus a negative sine y. And this is dy dx. You see the sine y is going to cancel out. Yeah. So that was neat about that one. And so the work left was not that much. This is just y dy dx. And then you can solve for that, and you'll get the answer 1 over 12. Okay? So stop there. Sorry to take you over 7 minutes, but that should complete us now for this section. I will shoot you in Blackboard the answers for that sample exam, and the test will basically mimic that. 10 problems, and the way I ask those questions is the same type of questions I'm going to ask. I just change the problem. It's the same question, okay? Thank you.